All right. Thanks everybody for coming.
All right, everybody, let's get started here.
This is one of the most energetic crowds I think I've heard in this room for a while. Great to see. So today it's my pleasure to introduce Brianne Anderson, who's been with us for about 2 years. I think you started in January?
Yes.
Yeah, a couple years ago. So 2 years of pretty much pandemic life in the department. But prior to that, Brianne comes to us from the Denver area, where she spent a lot of time up in the mountains. I was interested to learn that she's climbed 5 different 14er mountains. Well, in Colorado, I've done one of those, so that's a credit to you. Also, something that we used to do from Fort Collins, which I imagine students do here as well, is go storm chasing, but I'm not sure how many people have had the same success that Brianne had on her very first storm chase. She saw 6 different tornadoes, which is a record as far as I'm concerned. The other thing I'll maybe point out about Brianne is she's very excited about random facts, and if you've not been on the 15th floor and seen her office door, every week there's a fun fact of the week, and they're really interesting fun facts of the week, not just, you know, some random stuff. It's actually some of it quite scientific and historical. So I do encourage you to go up to her office at some point and take a look at the door. But anyway, I won't go on too much longer. Just sort of hand it off here to Brianne, who's going to talk about her master's research, which is working on trying to reevaluate and update the cloud detection algorithm used by the GFS model. And so I'll let her sort of talk a little bit more about the research.
And then, can you hear me in the back? Okay, great. So again, my name is Brianne Anderson, and I will be presenting the work that I did for my master's. It concerned reevaluating the current NCEP, or National Center for Environmental Prediction's clear or infrared cloud detection algorithm. Now, the rightful question you might be asking yourself right now is, why reevaluate? What could possibly warrant a reevaluation of the NCEP system? Well, the first is the age of the algorithm itself. It was developed for and during the age of HERS, or the high-resolution infrared sounder. This sounder has since been replaced by CrIS, which I'll talk about in a few slides. Additionally, an idealized NCEP clear sky scheme would have only clear sky points. However, missing data points, false cloud points, will reduce the quality of the model analysis and potentially produce a less accurate forecast down the line. Therefore, the overarching objectives of this presentation and of my project were to, number 1, propose techniques which could improve the NCEP clear sky scheme by removing cloud-contaminated points, and 2, identify more points with high certainty of clear sky to optimize data analysis and the assimilation. So in order to do this, I investigated and explored a few other algorithms, 2 of which I've included on this slide, which will not be discussed in this presentation, however, will be discussed in my thesis if you are interested. They are a dual regression method described by Wise et al. 2012, and then a method described by McNally and Watts, which is currently being used by the European Center. Again, I was going to tell you a little bit about what CrIS is. It is the successor to HERS, and it stands for Cross-Track Infrared Sounder. It is currently being flown as part of the JPSS, or Joint Polar Satellite System, and is currently being flown on SUNY NPP and NOAA 20. It has 2,211 spectral channels ranging from 650 to 2,250 wave numbers. And the field of view at nadir has a resolution of 13.5 kilometers. Now, for the purposes of my particular project, I only use data from NOAA 20. One of the other instruments on NOAA 20 is VIIRS, or the Visual Infrared Imaging Radiometer Suite. The purpose of using VIIRS in this project was purely for the visual confirmation of the scene. And because of the higher resolution, it could be used to really detect the minute differences in different cloud types, as well as because of the cloud composite, you could really see the differences between topography and clouds. And the nadir resolution of the VIIRS satellite is 750 meters, however, can be co-located with CrIS at 13.5 kilometers. In addition to the observed data, an algorithm also requires model data. And the model data that I used for my project came from the CRTM, or the Community Radiative Transfer Model. The Community Radiative Transfer Model is developed via a conglomeration of multiple radiative transfer models. A radiative transfer model works by inputting model data, running it through multiple radiative transfer models, and then outputting clear sky radiances and transmittance. With every single model, just as with all components of this project, there are errors that could potentially occur because it's an estimation. So please keep that in note when you are seeing the rest of this presentation. In order to kind of understand the NCEP system, I want to kind of describe what it does in this right now. However, I do want you to note that this is going to get complex, and it is completely fine for you to just maybe zone out partially. Don't zone out completely, just zone out partially while I show you some mathematical functions as well as kind of the general gist of the algorithm. So let's say that we have this field of view, and there's a 600 hectopascal cloud in this above this field of view. And then NOAA 20 with the CrIS satellite or the CrIS sounder will come in and take brightness, temperature, observed data at different wavelengths and at different wave numbers. Wave numbers associated with smaller values or smaller wave numbers are associated with higher up in the atmosphere. And it is this idea which is integral to the way that both of the algorithms that I'll be talking about use. Now, one thing of note is that once the observed data has detected the cloud, the observed brightness temperatures will be very similar to one another below the cloud. Additionally, the CRTM, or the model data, will produce a brightness temperature that is clear in a simulation at each wave number and at each pressure level, which there are 127 of. Then a clear sky, a weighted model clear brightness temperature difference is taken at each pressure levels, in between each of the pressure levels, called a pressure layer, and there are quality controls that are put into place in order to eliminate certain channels. And then we'll go through and we'll do a first weighted sum of the observed brightness temperatures at each of the different wave numbers, but at each of the different, summed through each of the different wave pressure layers, and addition to another sum. And those will be used to produce a cloud percentage, which will then in turn be used in this final weighted sum value. And this, at the very end of everything else, this is kind of what is being used at the very end product to compare against each of the different pressure layers. So it's kind of like, you see at the very bottom, we want to see if there's a cloud at that bottom. And the way that we test it is we compare it against the layer above it. In this first test, however, we have a 0.75, and that's an NCEP product relating to fog, or surface level clouds. Additionally, so if it doesn't match this, it ends up just leading to a cloud top pressure that is not within that pressure layer and is eliminated. Then it goes to each different layer, compares it against each other with this sum value, And if it finally meets this criteria of the lower layer being more than the upper layer, then we say that there's a cloud top pressure within that upper layer. And this keeps going, and for our case, let's say that we kept going, and it finally was accepted at this higher level where the X value, our pressure layer, which we are saying this cloud is in, it'll be accepted. So just in general, to sum up, and for those who were able to just zone out for a second, the way that it works is that it compares clear, model, calculated, and observed radiances at several different pressure levels from the surface to the top of the atmosphere. It uses only select CrIS channels after being run through a quality control, and there are 3 major assumptions made in order for this to work, which includes that the cloud is single-layered, so no multi-layered clouds, that the cloud has the same brightness temperature that the pressure layer that it's in, and that the effective emissivity is equal to 1. Therefore, we assume within the NCEP algorithm that clouds are opaque. The other algorithm that I would like to talk to you about today in this presentation is CO2 slicing. For lack of a better term, or more of a spoiler alert, this is actually the pinnacle algorithm that was used within the investigation. And again, I would urge you to read my thesis if you would like to know why this was selected. Just like NCEP, it compares clear, model, and observed radiances and assumes that there's a single layer of cloud top pressure. But it does not assume that the clouds are necessarily opaque. And it also uses only paired absorption channels. These absorption channels are so spectrally close to one another that the ratio of their effective emissivities is approximately equal to 1. And the work is done by comparing the ratio of the model data and the observed differences at spectrally close channel numbers to identify clouds. It is assumed that, again, the smaller the wave number, the more sensitive it is to higher up in the atmosphere. And a larger ratio potentially could indicate that there is a signal of a cloud, which I'll demonstrate again right before I show you, I'm going to show you these equations. This is the basis of the CO2 slicing equation. One thing to note is the IR window test, which is kind of the quality control catch-all of the full CO2 slicing equation. It is used to detect if there are any surface level clouds and to confirm, or more so, to actually provide a conclusive, definitive classification of a clear sky field of view. So let's go back to that field of view that we have, and we have that 600 hectopascal cloud top pressure, and we have nodes what to come in with CrIS and also veers, and then this is where there's a slight modification from maybe the original CO2 slicing equation. The way that I adapted the CO2 slicing equation in one way was to calculate the tropopause height and calculate the planetary boundary layer top height in order to identify regions where clouds typically exist. Now there is a possibility of surface level clouds. That'll be caught by the IR window test, but in general, this is what we are dealing with for the atmospheric profile. Again, the CRTM, the model, will produce a clear brightness temperature, but we use a weighting function in order to determine which one to use in each wave number. And note the upper left corner where that equation is, where the CO2 slicing equation occurs. So this is where we deal with the ratios. We compare the ratios of these two differences. So we have the CRTM at mu1, or wave number 1, and the observed radiances at wave number 1, and we do a difference, And then we compare that to the layer below it. Again, we are looking for a little bit high of a pressure level in order to detect if there is a cloud. Now, let's say in our simulated case that doesn't occur. So we go down to a second pair, which consists of the new 2, or the wave number 2, from the original pairing, and the current, or the new 3, which we'll kind of assume as mu 2. Again, let's say that this pairing was not sufficiently large enough to identify a cloud. Therefore, we go down to another pairing. And let's say in this case that this pairing was sufficiently large enough in order to identify a cloud. And because of that, we stop the equation. Unlike NCEP, where it continues to sum with each of the different wave numbers, CO2 slicing stops. However, if there isn't a cloud, there is a 5th layer that we use. But again, we have a cloud. And we compare it against our quality control and to detect if there are any surface level clouds that might be affecting just general atmospheric profiles. So, in addition to our different variables that the CRTM has to provide us for selecting the CO2 slicing equation, the last part that I'll talk about is this idea that we want this ratio, whatever pressure level that ratio is the closest to one another on either side of the equation, is where we assume the cloud top pressure to be. Again, we are using channel pairs, and the way that the original CO2 slicing equation worked is that it had a total of 3 pairs or 4 wave numbers. And it was because of the capabilities that hers had. However, now that we have CrIS and we have much more spectral channels to choose from, we can produce a ton more pairs. And the way that this works, and this is again an adaptation from the original CO2 slicing equation, is that let's say that we have this top grouping, and each one of these are going to be compared against that middle value at that 705. If, let's say, 690.65 and 691.875 compared against 705 meets that criteria, it is the average of those 2 values are taken. And it goes down into the atmosphere and also includes that IR window test, which the original CO2 slicing equation doesn't explicitly talk about. In order to analyze this data, so going from what we know from both of these algorithms, the way that it was analyzed and the conclusion was made that CO2 slicing was the best algorithm of the ones compared, we used a test day, and this was used on all of the algorithms, and it was done that way so that we could compare each of the different algorithms to one another. And again, we used collocated spheres in order to use as visual confirmation. And then we also use these observed minus model gradients FOV distributions, which I'll talk about in a few slides. So to kind of start off, we used a simple case, or a case in which there were several cloud types, but we wanted to eliminate any maybe variabilities that could potentially interfere with looking at each of the algorithms and their capabilities by themselves. So in order to do that, we used only day data, so when the solar zenith angle was less than 84 degrees, and only using ocean and in between 60 north and 60 south latitude to eliminate surface emissivity effects. Here's the pretty picture. This is collocated VIIRS, a composite image of true image data. And as you can see, there are lots of different cloud types. We're dealing with this lovely April day in this year. And you can see there are many different cloud types, many different features, and many different ways that CO2 slicing, and NCEP can determine the cloud's top pressures. Again, here's NCEP. This is what NCEP says as the cloud top pressure. The resolution that was made with the capabilities of MATPLAB is similar to what was used, or what the actual resolution of CrIS is. And do note that there are orbital track features that are just demonstrated on this image. Now here's the exciting one. This one's CO2 slicing. As you can see, just toggling back and forth, there are many differences. But there's one point that I want to, or one area that I want to kind of zoom in on to demonstrate the capabilities that CO2 slicing has over NCEP. And we're going to zoom really into this visible data. We have our CO2 slicing, and we have our NCEP, and a little inlet if you would like to know your bearings. So there's this feature on the Beers image, which is the sun glint. However, sun glint is only affected by the visible spectrum and not the IR spectrum, therefore it can be ignored just in general. But let's talk about the Cirrus Clouds. You can kind of see it on the visible, and you can see that NCEP and CO2 slicing both picked up these clouds that were higher up in the atmosphere, most likely cirrus. Cirrus are a major issue or major concern within the clear sky scheme because optically thin cirrus are hard to detect. That is because they're optically thin, NCEP doesn't pick them up. As I said, the emissivity is assumed to be 1, and so NCEP classifies that field of view as clear when there is a cloud affecting it. However, CO2 slicing doesn't. Therefore, it is identifying substantially more cirrus clouds that are potentially, or I would argue, optically thin that would have affected the NCEP algorithm, but doesn't affect CO2 slicing. One way that NCEP could be improved utilizing CO2 slicing. An additional point that I want to point out is a clear sky field of view. So this one is our visible. You can see no clouds. CO2 slicing is not picking up any cirrus that are optically thin, but NCEP is marking it as a mid-level cloud. This would also be a cloud contamination in the NCEP clear sky detection scheme. Again, I was going to talk to you guys about these observed minus CRTM or model data plots. They show kind of the accuracy of the clear FOVs detected by each of the algorithms, noting that there are random errors and everything else that could potentially cause a distribution such as this. So if you have the observed brightness temperature and the model calculated brightness temperature, clear brightness temperature specifically, if those two are similar, aka the difference is close to 0, then you're dealing with a clear FOV, or field of view. Again, a large difference would indicate a cloud. For an idealized algorithm, you want a long, skinny, symmetrical curve on 0. And the symmetry is very important in that we want a distribution that has the random errors equal to each other on either side. We also have this feature called a cold tail, and this happens when several field of views that are marked as clear, but actually have, or but are actually cloudy, are incorporated into the algorithm. And these field of views would cause cloud contaminations to the NCEP algorithm and the assimilation in general. For an optimizing of this assimilation, we want no cold tails, and we want a sufficiently large amount of these near zero values, indicating it selected proper data with just random errors or just errors in general that are assumed within this scheme. This is what was shown for the highest wave number, or the highest wave number grouping in the CO2 slicing equation. They look very similar to each other, this NCEP and CO2 slicing, CRTM, or OBS minus CRTM plot. They both have that symmetry on 0, and this is very typical of this wavelength, or this wave number, because this wave number is mostly clear. You're not going to see a lot of clouds higher up in the atmosphere, and because this wave number is associated with and more sensitive to higher up in the atmosphere, you wouldn't typically see a large count of field of views that are classified as cloudy. However, if you go lower down in the atmosphere at the 715 wave number channel, they both have very similar shapes. However, the CO2 slicing doesn't have what NCEP does, which is that pulled tail. And this would cause concern within the NCEP algorithm because it's accepting those values. However, because there's that warm tail, it's less of a concern within this particular wave number. However, when you look even further down into the atmosphere, where fewer clouds or fewer clear field of views would be detected anyway, there still are an amount of clear FOVs, or field of views, that are not being detected by NCEP, but are being detected by CO2 slicing, and they are centered about that 0 value, indicating that NCEP may be too conservative, may be losing data that CO2 slicing has identified is usable. And we also have that cold tail. This one is a significant cold tail in that it's allowing that many field of views, NCEP is allowing that many field of views into the algorithm that are actually supposed to be cloudy. Again, 3 times the amount. Now, I didn't want to just stop there. I wanted to look at a global scale. I wanted to make sure that just because I wanted to check with a simple case, I wanted to make sure that it worked at a global scale. That means adding in the land, which is going to affect the surface emissivity. That's adding poles, that's adding night, and on a new day. So seeing that it's working on all different fronts. And if that is the case, if we can say that the complex case and the simple case are similar enough to each other, then topographic, temporal, and latitudinal variability is limited. So as a reminder, this is what that CRTM, or the model and observed difference plot, looks like at the 715 wave number with the simple case. And this is the complex case, that global model using all latitudes, all land types, full 24 hours. And you can see very few differences between the simple case and the complex case, indicating that this CO2 slicing algorithm could potentially help NCEP at a global scale. NCEP has a huge cold tail that is not seen within CO2 slicing, and there are 2 times as many, probably certain, field of views that CO2 slicing picked up that NCEP did not include within their algorithm. This is valuable data that is not being incorporated into the algorithm. Again, this is just our beautiful field, or our beautiful picture at the 31st, or at the 30th of July. This is what NCEP says. Again, it's a little more complex with the land incorporated into the algorithm. And then this is CO2 slicing. Again, I'll toggle between the two just so that you can highlight differences. But again, I want to highlight 2 areas where CO2 slicing was exemplary. The first is this one over land. As you can see, there is this clear field of view identified by both FIRS and CO2 slicing, but not by NCEP. NCEP identified that field of view as cloudy, which would have affected which is a point that could have been incorporated into the NCEP algorithm, but wasn't. And then look at this polar region. There are 2 points, and I'll do them in succession to one another, in which NCEP said that there was a much higher level of cloud than maybe was actually there. And this is because with the polar surface, there might be surface effects causing issues to the NCEP algorithm in general. So in general, here are some conclusions to take away, hopefully, from this presentation. And the first one is that even with these several places of errors, like the model data could have errors, the satellite could have errors, I could have potentially done something wrong. CO2 slicing still could enhance NCEP by enhancing their clear sky detection. CO2 slicing suggests that NCEP is using cloudy field of views as clear, as indicated by those pulled tails. But they're also missing valuable data, substantially so, that could potentially be part of the clear sky scheme. And this is identified by the smaller histogram peaks with NCEP versus with CO2 slicing. Additionally, adding 22 channels could enhance finding a more accurate topological pressure, and CO2 slicing, while it still needs work over certain types of topography such as deserts, it does well over ice, which is surprising. And the complex model suggests that the CO2 slicing may be able to work better than NCEP, even in the most challenging conditions. So what's the next step with this project? The first big one is for it to go into operations, or for it to be tested to see if it actually improves the NCEP system. On my end, I will be doing a couple more test days to ensure that the data and the information that was collected from this presentation and just in general are incorporated in these other test days. And that's kind of where my position stops. I will be eager to see what NCEP does with the assimilation and with the findings in this presentation. But I will be joining Mike's team, their VolCat, or Volcanic Cloud Analysis Toolkit this spring, which I'm genuinely very excited about. The last thing that I'll mention are quite the number of people that have helped me with this project, including several collaborators that have worked behind the scenes, different funders. I want to give a huge shout out to Jim Jung, my PI, Paul Menzel, Sharon Abuda, both all part of my research team. Grant Petty and Tristan for being part of my academic, part of my master's panel, and a lot of friends, but probably the most important person that I have to thank is my mom. And then second and third are my sisters. You can choose which order that goes in. But again, thank you so much for coming to this presentation. I will open it up to comments or questions. If you have anything that you want to email me about, that it might be like a little bit too extensive to directly address in this presentation, please do email me. But again, thank you so much for coming, and I will open it up to comments or questions.
All right, any questions for Brianne?
Yeah.
I have just a really quick question.
Yeah.
I was wondering what the size of the field of view was for the satellite.
Yeah, so it should be the 13.5 by 13.5 resolution.
Okay.
Yes.
And then I was just wondering
Yeah.
what happens when there's clouds in part of that field of view, but not all of it? Like, is there a threshold where it starts detecting that?
I'm not 100% certain. However, I believe it depends on the brightness temperature within the field of view at the different levels within the atmospheric profile. So if the detection from the model data or from the observed data is indicating the cloud versus the clear area, that'll be determining how it'll affect the algorithm in general.
Thank you.
Yes.
have a question regarding cases you chose. They were primarily the exemplary cases, and at the end you briefly mentioned CO2 slicing doesn't work very well over the desert. So I was wondering if you could maybe comment on maybe some of the things you see in a case where it's not exemplary and that might be actually performing better.
Yeah, so there are a few points in which NCEP did better in detecting, and it was kind of determined through just like a very simplistic overview that there were a couple of points that over desert regions, because of the effective emissivity issue, that would produce those cloud detection, something that's not necessarily as accurate as what NCEP said. I don't have a specific example for you in this presentation, but it is something that I would be willing to share in email. Yeah.
Yeah, so can you go back to those ones where you were showing the global maps with the differences between the NCEP and the
You want just
CO2 slicings? Yeah, so when I was looking at those between the two, it looks like the CO2 slicing did better with the high clouds.
Yes.
And I was just wondering if you can kind of touch on why exactly NCEP had a hard time with getting those high clouds where the CO2 slicing did a better job, and physically what's happening there.
Yeah, so there are two things to consider. First off, that CO2 slicing could be incorrect in the identification of certain clouds in certain regions. But because CO2 slicing doesn't assume that effective emissivity or that the effective emissivity is equal to 1, so there's an allowance of these less opaque clouds, you can detect things like those thin cirrus. So because of those thin cirrus, which may not be detected from the NCEP algorithm, like maybe in this region right here, but are being detected from CO2 slicing, that's a consideration that these might actually end up being those more opaque or more optically thin cirrus. The other thing to consider is that CO2 slicing uses just a few channel pairs. So if it does pass the first test, as demonstrated in the diagram or the display that I showed of the example, if it passes that first, or if it agrees that there's a cloud at that one point, then CO2 slicing stops. Whereas NCEP, that is one situation where NCEP might say, I'm going to continue down.
Also, kind of a follow-up on that,
Yeah.
I was wondering if the algorithm uses any mirrors channels as well.
Not that I'm aware of, but I can get back to you on a definitive answer to that.
So if I understand correctly, the method is based on comparing the CRTM calculations with the observed radiances.
Yes, correct.
And I assume the CRTM calculations require some prior knowledge of the temperature profile. So I guess my question is, how sensitive is the algorithm to getting that profile right, and does it have maybe particular problems if you go to a polar region where you've got an inversion that may be a little hard to resolve
Yes.
from other sources of data?
So, for instance, looking at these plots right here, at the observed minus CRTM plots, this skew from 0 may be an issue with model data being incorrect. And that is one of the just byproducts of a generalized error within each different component. So this is a complete possibility that the reason why it's not exactly on 0 or set onto 0 is because there are some model data errors.
Thank you.
Yeah.
For your more complex case, you were using all latitudes. How would you go about choosing a day?
So the question was how was the selection of the complex case made in general, and why that particular date was selected. It was partially selected because there were a couple of test days that my research team very generously provided me. But the other reason is that this particular one had a lot of different cloud types, and it was also during a summer month for the northern hemisphere and winter month for the southern hemisphere. So that's kind of an added feature that wasn't explicitly discussed about, but is definitely of interest to the selection of that day. Yeah.
First of all, your answer to Grant kind of answered one of my main questions, which or alluded to it, which is about this offset from zero. And it seems from your figures that maybe the CO2 slicing then might be a little more sensitive to the model profile
Yes,
than the standard algorithm.
that is a correct statement.
Is that because does the standard, I don't remember from the beginning, does the standard algorithm use more channels or less channels with the CO2 slicing?
It depends, I guess. I guess if I were to give just an overarching statement, I would say that potentially NCEP uses more. It goes through, the selection of the channels is due to the quality control tests. And in most cases, to the best of my knowledge, it is more than CO2 slicing is using. However, they're using different different bands as well. So that's one of the limitations that CO2 slicing potentially has, in that it eliminates certain other wave bands and only specifically looks at the absorption bands relating to CO2 slicing. Yeah.
Right now, is the only way for you to determine which one is more correct is to looking at the Beers like image? Just a visual inspection right now?
So using these, the observed minus brightness or observed minus model data plots, that's one way to kind of determine what the classification is with the clear versus cloudy field of view classification. However, there is a determination that was not explored within this presentation, but looking at the amount of difference between the cloud top pressures. That's something that I'm investigating. Within this past week, I've been investigating, looking at the specific ranges. If there was a cloud detected, what NCEP said, what CO2 slicing said, see how far away they are from one another. Okay, well again, if you have any further questions, I'll leave it back on this slide that you can take a picture of my email. But again, thank you so much for coming. And yeah.